For a second order electrical network, we in the first few topics we derive the transfer function of some electrical networks. We have RL and RC circuits. Those are first order systems. Now, if we want to solve for second order electrical systems, the the basic example of this in electrical network is if you have R, L, and C circuit. So if you have the resistance here or resistor is a linear resistor, it's not non-linear. We have an inductance inductor, then we have capacitor here. Then if we apply a voltage at this circuit, RLC circuit, so let's say this is small e, then this is R, this is C, and this is L. Now, if we want our output to be, it can be the voltage across the capacitor. It should be L, and this should be C. Or also, just like what we did before, we can also take the current as our output. So you can choose your outputs, but our input will be is of t. So let's say is of t is our input and I is our output. And derive the transfer function of this RLC circuit. So using Kirchhoff's voltage law, so we have applying Kirchhoff's KVL. So this will be E of t, then minus I, the voltage across the resistor, I times R. Then minus the voltage across the inductor, that is L di dt. And lastly, the voltage across the capacitor, that is 1 over C, the integral of I dt. And this is equal to 0. Then assuming no initial conditions, we start at t equals 0, then the inductor is uncharged conditions. And also the capacitor is uncharged. And we cannot take the Laplace of this differential equation. So we have E, then I times R, then this is derivative L times S of I, then this is the integral, so 1 over S C times the current I of S, and this is equal to 0. Then rearrange the circuit or the equation, then factor out I at the other side. So we have here R plus L times S, or SL, then plus 1 over S times C. And output over input. Our output is, remember, our output is the current. So this will be I all over E. So we just take the inverse of this 1 over R plus SL plus 1 over S T. And again, we need to make it standard by multiplying. We can multiply S so that the S here will cancel out. Then we also need to divide it with L. We need to divide it by L. So S over L. So that this will be S over L all over, we have S times L times S over L. This will become S squared. The L will cancel out. S squared. And we have R times S over L. So that will be R over L times S. Then this one will become, this S will cancel out, so 1 over L times C. So this will be our transfer function. Then if you want to determine the different parameters, that just like what we did in the previous examples, we want to determine the natural frequency, omega n or omega naught. This should be equal to the square root of this. This should be equal, this should be our omega n squared. 1 over LC. 1 over L times C. So to solve for omega n, natural frequency is just equal to the square root 1 over the square root of L times C. For an RLC circuit, then for the damping ratio, zeta, 2 zeta omega n, this should be equal to the middle term, which is R over L, R over L. So solving for zeta, zeta will be equal to R over L times 2 omega n. And there is another factor here. This part, R times 2 times L. This is what we call the Neper frequency. Some references, the symbol that they use is alpha. So alpha is equal to R over 2 times L. So if we write this, zeta, or the damping ratio, will be equal to alpha, the Neper frequency, divided by the natural frequency. And if you don't want that Neper frequency, we can still derive our zeta in terms of RLC. So this will be zeta equals R all over 2 times L times omega n, which is 1 over the square root of L times C. Then we can simplify this. Zeta will be equal to R over 2. Then we can put L inside. It will become L squared. So square root of L squared divided by L. So it will become L over L, or L over C. And if we take the inverse of that, because this is 1 over 1 over, this will be equal to the square root of C all over L. So this is the formula for the damping ratio of an RLC circuit. So this is how we derive the transfer function of an RLC circuit with the current as our output. You can also do the voltage across the different components here as your output.